Hello everyone. So this is our last video, 30th video. So you made it, almost made it. And in our last topic, we have kind of two applications to economics of definite integrals. This hopefully won't take terribly long, but there's two kind of things that are good to cover. So the first topic is, first application, oops. Is the idea of consumer surplus. Okay, so in this situation, we have a demand curve where price is a function of function f of x, where p is the price at which you can sell x number of items. So we've kind of thought about, this is our third time talking about a demand curve in this class, and perhaps it's we've kind of talked about it in different ways, so it might be a little confusing, but this is the way we first talked about it, where we write the price is a function of the items you can sell at that price. And the last thing we talked about was the elasticity, and we wrote it the other way. We wrote it, the number of items, we wrote it as a function of price instead. So we're kind of going between those two things. But in this case, we're writing it as a function of items, of X items you can sell at price P. So the price, in other words, this gives us the price at which we can sell these X items. Okay, now again, if you sell more items, the price has to go down. So this is in general a decreasing function, right? So as a matter of common sense, I guess, if you want to sell more items, the price has to go down. So the function P equals f at x is a decreasing function. So there's different possibilities for this, but we can. So this is x number of items sold on the x-axis here. So we can kind of sketch it out. One possible way it could look is something like this. So this would be price P on the y-axis. So some kind of decreasing function like this. Now, we live in a system where you have a fixed price for everything, right? Well, not for everything, but for most things, you have some kind of fixed price. So you might be willing to pay more or less than the fixed price that you find at the store, depending on how badly you need something. But there is a price at the store, and that's what you're going to pay. You can't barter in our economy, right? It's not a barter economy. It's a fixed pricing economy, right? So for example, like you can imagine that like at the end of the pandemic, you may really want to take a trip. You may really want to go to Hawaii. You might be willing to pay like $1,000 to go to Hawaii, right? But the tickets to Hawaii might cost like instead $300. So they say this is like 300, right? But you could be willing to pay something like $1,000, somewhere higher up on the demand curve, right? So, however, you're paying 300. But what I want to understand is like even though you're willing to pay more, you're actually saving money in this fixed price economy. And the amount you're saving is given by these blue shaded area of the curve. So what I shaded in blue here. So for example, tickets to Hawaii. 300 is probably really cheap, but let's just say 300. Maybe it's a deal after the pandemic to get people to fly again. Costs $300 after the pandemic. And let's say they sell, I don't know, capital A tickets, number of tickets. And at $300, they sell, the airline sells $300 times A tickets. So it sells A tickets. It sells A tickets, making 300 times A dollars. Okay? I'll put the dollar sign here. Now, like I said, though, you're really desperate to travel, so you might have been willing to pay as much as $1,000 for a ticket to Hawaii. So what I want to compute is like the surplus you're getting by having this fixed pricing, like a controlled pricing, rather than just the ability to pay by what your demand is or what you would barter for in a barter economy. And that surplus is this area in blue. It's the difference between what the airline's actually making now, which is the purple shaded rectangle, right? And what all the consumers would be willing to pay if you were just allowed to set the price given your own demand, which is this area shaded in red. So that difference between what the airline's making now and what consumers would be willing to pay, possibly, if they were allowed to just barter, that difference is the blue area. That's called the surplus, the consumer surplus. So the difference between what the airline would make if consumers could barter according to their demands, their level of demand. Like you really, really want to go to Hawaii, so you're willing to pay more, versus what the airline, the price, what the airline makes with fixed pricing. I mean, fixed in quotes because the price has changed, but it's somewhat fixed. With fixed pricing is called the consumer surplus. So that's supposed to be what the consumer is getting out of having a modern fixed price economy versus a barter on demand economy. It is the area shaded in blue above. Okay, so what I want to do is compute. Now we want to compute this area shaded in blue. So maybe I should kind of take this guy, copy it. Do that again. I don't want to copy it over a page break because if you print it out, it'll be a mess. Okay, well, that's better than nothing, I guess. See below. Can you move this? Okay, there we go. There we go. Perfect. Perfect. Okay, so our goal is to compute this surplus. This is supposed to be the price here. Our goal is to compute this surplus. Okay, so we can actually do this quite easily within our current knowledge of how to find the area between two curves, right? So this is just the area between the demand curve and the rectangle of height, in this case, 300, on the interval x equals 0 to x equals I. Okay, and so we know how to do that. So remember, this curve is f at x. So the area, we take the difference of the area under the demand curve and the difference of the area of the rectangle, right? That's how we do the area between the two curves. Sorry. So in this case, using our knowledge of how to compute the area between two curves, we can compute the surplus to be the integral from 0 to this number a, the demand curve minus their 300, right? Because the rectangle is just the area, the function that defines the rectangle is the constant function, height 300 dx. And so this is how, I mean, 300 was just an example, but in general, this can be any price, right? That is the fixed price in the market for whatever, whatever quantity, commodity you're interested in. Okay, so this example is easily generalized. So definition, the consumer surplus for a commodity having demand curve P equals f at x is 0 to a, integral from 0 to a, f at x minus b dx, where a is the quantity sold or demanded at price b equals f at a. Okay, so if you like to memorize formula, this is the formula, and these are what the symbols mean, right? And the f is the demand curve expressed as a quantity of number of items sold rather than prices, which is what we were doing with elasticity. So that part's annoying, but that's life. However, this is why it's called a surplus. This is why this area is called a surplus, because it represents what the consumer is saving in an economy with fixed pricing rather than a barter economy where they can get, you can get carried away and be willing to pay for something more than you should be paying for it, or than you could be paying for. So, however, that's the idea. I think it's a cool idea. Maybe the implementation of this formula is not as exciting as the idea. So I wanted to go through the idea, and then now we'll do an example. Okay. Find the consumer surplus for the following demand curve at the given sales level X. So in this example, this is going to be very mechanical. The demand curve f at x is going to be x squared over 200 minus x plus 50, and the sales level A is going to be 20. Sales level A, capital A. Okay, so let's do this. So according to the above definition, we have the following. We have the surplus is the integral from 0 to 20, this f at x minus b dx, where b is the value, it's the price when you're selling 20 items. So we have to first compute b to really be able to do this example, right? So to be able to do the computation. So we need to first compute b. Before doing the integral. Okay, so let's see. So I should copy this guy, I guess. So b is f at 20, which is 20 squared over 200 minus 20 plus 50. So 20 squared is 400. So that's 400 over 200 minus 20 plus 50. 400 over 200 is 2. So it's 2 minus 20 plus 50. So that you can compute, but that's 32. Okay, so the integral we need to do is then integral from 0 to 20. The fx is, I'll just write it in here now. It's above, there it is. Here. So fx minus b. So fx squared over 200 minus x plus 32. Oh, sorry, plus 50. Then minus 32 dx. Should simplify this. So this is 0 to 20 integral x squared over 200 minus x and 50 minus 32 is 18. Clean that up a bit. Okay, so now this is as simple as it's going to get, and we can do this integral fairly easily. And so again, I'll do it all at once. So the antiderivative of x squared is x cubed over 3. Of x is x squared over 2, and then of 1 is just x. You get the antiderivative of this whole thing is 1 over 200 x cubed over 3 minus x squared over 2 plus 18x. Evaluated 20, subtract the result of 0. This is a bit annoying. You might want to use a calculator to do this. So this is going to be 1 over 600 times 20 cubed minus 400, which is 20 squared over 2, plus 18 times 20, and the limit is 0. If you plug in 0, you just get the bottom limit is 0. So if you punch all this out in the calculator, you get $173.33. $173.33 is the consumer surplus for this quantity, when it's being sold at a price of $32 for 20 items are being sold for $32 each. When 20 items are sold for $32 each. Okay, so that's what I'm going to say about consumer surplus. You can play with it more in the homework, and I'll be happy to go over more examples with you in the live meeting, of course. So the last topic is estimating the future value of a continuous income stream. Okay, so this is a little bit weird, and it's even kind of harder for me to explain. So intuitively, but hopefully I'll give you some sense for what this all means. So recall that if we invest P dollars at an interest rate of R% in a savings account compounded continuously, then after T years, we have F of T equals P, I should say amount, maybe A of T is P ERT dollars in the account. Okay, so that was what we saw for like computing interest compounded continuously, is this exponential growth of the balance of the account. So in this situation, we're going to do something different. We're not going to just, so this involves investing upfront a principal P dollars, right? That's what I call the P, it's the principal. But say like you can't invest like $1,000 or something like right up front, but you want to, you have a certain time horizon. You're like, okay, over the next 5 years, I can invest $1,000 and I'll deposit I'll deposit money in the account each day. And then that will get compounded continuously at a certain interest rate R over the 5 years. And at the end of 5 years, I will have put a total of $1,000 in the account. But of course, you'll have more than $1,000 at the end of 5 years because you'll have been earning interest continuously on the money you're putting in the account gradually over that time. Right? So it's kind of a very different situation. So instead of putting everything up front, you kind of say, I'm going to put $1,000 in over 5 years. And so, so today I'll put in, what is that? I'll put in $20 today, right? Or something like that. I have to think how many days are in 5 years. It's more complicated, but I put a certain amount every day so that I get to $1,000 in 5 years. And as the money is continuously earning interest rate at a rate R. Now the question is, how much money do I make at the end of the 5 years? Okay, so that's what we want to answer. So I'll write this up. Now suppose instead of putting all the money in, your entire principal in at the very beginning, you invest it over the course of capital N years, right? So over the course of capital N years, you will have invested your principal P. So it's not really called a principal in this case, but I'm trying to build the analogy anyway. And the way this is done, and this is done by putting in equal amounts of money. This is done by putting in equal amounts of money each day. So this is maybe for some people like a better investment strategy because you're not having to throw up all this money up front, right? You may not have that disposable income, right? And then the money in the account earns interest at a rate of R% compounded continuously. Okay, so the question is, how much money do you have in the account at the end of the N-year period of capital N years? Okay, so that's what we want to try to address, right? Now, it's not the same as the other case, because the other case, you're throwing all the money in the beginning, you watch it grow exponentially. This, you're putting it in every day, and it's growing in some way exponentially every day, but it's not all the money is growing for the same amount of time. That's what makes this tricky, right? So like, you put in some money at the beginning, like say you put in 20 bucks on the first day, it will grow for the entire period, continuously compounded interest. But maybe on like the last week, you put in like the first day of the last week, you put another $20, that only grows for a week. It only earns interest for a week. So how do you figure out like how much money you have at the end when different amounts are earning, different amounts in the account are earning interest over different time periods, right? So this seems actually quite complicated. And it is a complicated problem, and it's not something that we can answer exactly because it's kind of mixing a continuous phenomenon with a discrete phenomenon. You're putting in money in discrete amounts, like say so much each day, but the interest is being compounded continuously. So we can't answer this exactly, but we can estimate it. So answer, we can use an integral to estimate this amount. The amount in the account after N years. But this is only an estimate. And the estimate is the integral from 0 to n, the principal e to the r, the interest rate. So it looks a lot similar to the usual compound interest formula now, but here's where it differs. The number of years minus t dt. Okay. So the reason is, and the big difference is this n minus t, because like I was saying, you're investing it over this period of time, and not all the money is growing over the entire period of time. At some point you invest at a time t, you put in a certain amount of time t, it will only grow for n minus t years. And so that's what this factor in the exponential is taking account of. And that's very different from the usual continuously compounded interest where it's just growing, the whole principal is growing the entire time. Okay, so but then this is also kind of an estimate because you're not investing the principal continuously. It's invested in discrete amounts each day over the period. But that's really hard you can't mix apples and oranges, so we can't do that exactly. Okay, so anyhow, these are kind of subtle things, and I'd be happy to address, if you're interested, to address more in the live meeting. But that's how we deal with this kind of situation. And in some ways, it's a more practical situation for people than just investing all this money up front. But you'd have to compare what you get. Okay. Excuse me. Make sure I have all the pieces together here. Oh, I should say, so maybe I wasn't clear about this. So P is the principal invested I didn't say this quite right, invested per year. Okay, so it's not over the n years, it's what you're investing per year. And so over the n years, you'd have n times p. Okay, so here's an example, and let's see how this works. Oh, before we can, so okay, there's another problem. So before we do this, right, this kind of thing is an integral that we haven't maybe seen before, right? We haven't talked about how to do an integral of e to the k times something minus t. We've done e to the minus kt, that we know how to do. We've done e to the kt. We haven't done something like this. So we need to understand how to do an integral like this. So before doing an example, we need to understand how to integrate something of the form e to the ax plus b. Okay, this isn't hard actually. So what you do is you recognize that law of exponents comes really in handy here. So you have e to the ax plus b. This is e to the ax times e to the b. Right, that's just you multiply two exponentials, you add the exponent. So it's wonderful laws of exponents. And well, you remember, okay, as far as x is concerned, right, this is like a constant. So this is a constant, does not depend upon x. So if we go back to the integral here, we have e to the ax plus b dx is e to the ax times e to the b dx. But e to the b is a constant, it's just a number, there's no x in there. So we can move it outside the integral, ex, a to the x dx. And then we know how to do the integral of e to the ax. That's one, we've done e to the kx, but this is e to the ax, it's the same thing. So it's e to the b, e to the ax over a, right? Plus a c. And then to look good, we can put the e to the b back in there. So it's e to the ax plus b over a plus c. So to summarize, we have a new integral formula. We have e to the ax plus b dx is e to the ax plus b over a plus c. Okay, so that will be very, very useful. This formula will be very useful in dealing with the integral we have here, right? In the estimation of the continuous income stream. Okay, so let's do an example. So now we can actually do an example. So, okay, suppose that money is deposited daily at an annual rate of $2,000. So in other words, at the end of a year, you'll deposit $2,000. So at the end of 1 year. If the account pays 6% interest compounded continuously estimate how much will be in the account at the end of capital N years. Okay, so this is a lot of information. So we have to go back to the formula. I'll go back up and copy it and bring it back down. So okay, so now what do we have? So P, remember, sorry, cat pictures. More cat pictures. That's my life. Okay, so speaking of the devil, there he is, over there. P is the amount invested annually. So in our example, we have P is $2,000. R is the interest rate. So that's 6%, so we have to convert that into a decimal, so it's 0.06. And capital N is the number of years that we're interested in as investing the money for. So this case as 2. So the integral we're going to get to estimate the amount at the end of 2 years is the following. So we need to compute the integral. So to estimate the amount, after 2 years, we need to compute the integral 0 to 2, integral 0 to 2,000 e to the 0.06 2 minus t dt. Okay, so there it is. Now we want to use the new formula, so it's good to kind of do a little simplification. So I can pull the 2,000 out of the integral. I can always do that. And then I get e to the 0.06 times 2 minus 0.06t dt. You can kind of simplify that a bit. So I get 2,000 integral from 0 to 2 e to the 0.06. Oh, sorry. So 2 times 0.06 is 0.12. Right, so just think 2 times 6% is 12%. Minus 0.06 t dt. And if you like, I could just rewrite it a bit. So 2,000 integral 0 to 2 e to the minus 0.06 t plus 0.12 dt. And now this looks like it's in the form integral e to the at plus b dt, where the a is minus 0.06 and the b is 0.12. And so then we said, well, what we said that above, that this integral is just e to the at plus b over a and then plus a c. But if we're doing a definite integral, we just use an antiderivative. We don't have to worry about the plus c. So let me just clean that up. So using that formula, we're going to get that this is 2,000 e to the minus 0.06 t plus 0.12 divided by minus 0.06. And then just, what was the 0 to 2? Now we have to do some evaluation. Okay, so this is 2,000. If you plug in 2, you get e to the minus 0.12 plus 0.12 over minus 0.06. And you subtract, if you plug in 0, you get e to the 0.12 over minus 0.06. This looks kind of messy. It's not that bad. So you get 2,000. So this negative, you can bring it up top. So it's, and notice here you have, right, e to the minus 0.12 plus 0.12, that's just e to the 0, which is 1. So you have just minus 1 over 0.16 plus, because you have a minus and a minus gives you a plus e 0.12 over 0.06. And now you have to plug this into your calculator. And if you do that, you get approximately what do you get? You got approximately $4,249.90. So there will be approximately $4,249.90 left in the account after 2 years, or not left, I mean, in the account, as long as you're taking money out. This will be approximately $4,249.90 in the account after 2 years. Okay, so I think I'll make sure that there aren't any big boo-boos here. I think we didn't, everything is good. So I hope you enjoyed the class. I know this was a very weird time with COVID and all this crazy stuff that happened, and I was unable to meet any of you in person. And I'm glad of those of you I did meet and interact with in the live meetings. It was a lot of fun for me, so I hope you enjoy it too. But this is the last video, and so I always used to do this on the board in the old days. It'd be 4 times the end of the course. So that's the end of the material for the course. We have one more test and then the final. So after you're done watching this video, you should be able to do all the homework and all the quizzes that are posted on Pearson. And then you're good just to, after you've done all of those, and if everything goes well, you're good to start reviewing and getting ready for the 3rd test and then the final. All right, thanks for tuning in, and I'll see you in the live meeting. We still have some of those to come.